Welcome. This presentation discusses an analysis of well interference and innovative assessments of proper well density for the Osage Formation. My name is Matt Freeman. We will begin by describing an integrated study of a 6-well pad in the stack play. We will then move on to discussions of the flow mechanisms in the Osage and Meramec formations, respectively. Then we will discuss the implications of these findings. Today, we will discuss the results of a project involving 6 wells in the Meramec and Osage rocks of the stack play, which were observed to exhibit anomalous water production behavior with a nearly 100% water cut at high rates for over 10 months in the deepest wells in a wine rack pattern. A reservoir simulation-oriented integrated study was performed to diagnose the cause of this water production behavior, and a conceptual and simulation model involving high conductivity flow conduits was developed, which explains the observations. This history-matched simulation model was subsequently used to perform sensitivities and forecasts in an effort to determine an optimal development strategy for this area of the stack. In this specific area of the stack, it was noted during drilling that there were significant mud losses. During hydraulic fracturing of these wells, it was noted that there was effectively zero breakdown pressure for multiple stages in each well. And finally, there was significant evidence of faulting from the seismic interpretation of this area. The geological model predicts faults crisscrossing the area and places specific faults intersecting these wells in particular. NITEC's objective is to provide decision support for management using advanced reservoir engineering technologies. The workflow employed in this project was the standard NITEC approach for unconventional reservoir systems. We undertook an integrated reservoir study beginning with the integration of all pertinent data, including geological and petrophysical data, completions information, fluid properties, and well history into our proprietary Lynx software suite. An integrated 3D reservoir model was constructed using static reservoir properties and geomechanical data from the geological model. The reservoir model was then calibrated to history match the historical oil, gas, and water rates and bottom hole pressures for these wells. We leverage our vast experience with unconventional reservoirs and reservoir data integration to build a consistent, integrated model out of multidisciplinary data. Subsequent to the incorporation of the geological, petrophysical, geophysical, and well history data into the model, the process of history match calibration begins. The primary focus of the NITEC approach to history matching is the calibration of the hydraulic fracturing response of the reservoir system. Hydraulic fracturing is simulated stage by stage, utilizing the historical injected fluid volumes. The 6X reservoir simulator captures the dynamics of rock breaking via tensile and shear deformation, and provides options for proppant transport simulation. Subsequent flowback of the fracturing fluid is simulated as well, along with the long-term closure of the induced fracture network. Optimizations for field development strategies for the reservoir can subsequently be performed, usually including well target landing zone, well spacing, and injection volume. A major advantage of the NITEC approach is the integration of data from all available sources via the Lynx platform. Lynx was developed by NITEC to specifically enhance the workflow of reservoir modeling and simulation. Finding inconsistencies in data sources is made straightforward via the process of collecting and integrating the data, including bottom hole pressure measurements, induced microseismic data, well injection and production histories, and core calibrated relative permeability curves. The final calibrated history-matched model was a 3.2 million cell dual porosity 3-phase simulation model with the Osage and Meramec properties populated from the log and seismic data calibrated geomodel. Discrete fault planes every 1,000 feet along the wellbore were added to the Osage model to provide flow paths to explain the dramatic slumping of water into the deeper wells. In the course of building the reservoir model, it became clear that we would not be able to obtain a good history match under the typical conceptual model for unconventional reservoirs, where we have a zone of rock around each well which has been hydraulically fractured. The typical stimulated reservoir volume would correspond to the zone outlined in yellow, and under normal circumstances, this would be a zone of tensile and shear fracture generation and dilation, and these induced fractures would then be propped by the injected proppant, and this would be where most of our hydrocarbons would come from. Applying the typical SRV paradigm could not explain the degree of water segregation between wells observed in this study. Recall that our aim is to explain the long-term 100% water cut in the deeper wells. In order to capture this behavior, we needed to add distinct high conductivity flow paths so that the fluids could communicate vertically and laterally between wells and undergo buoyant equilibration inside the fracture system. Water injected in shallower wells drains into the deeper wells, and hydrocarbons entering the fracture system in the deeper wells floats upward into the shallower wells. Note that these two fracture systems, the typical SRV system and the high conductivity fractures, are connected, and this can be thought of as a triple porosity system. We see here a visualization of the water saturation in the fracture porosity after 6 months of production. Again, this is a dual porosity reservoir simulator, so for every grid cell there is a corresponding matrix and fracture cell. The fracture porosity is where the fluids are flowing. Here we see that the water has drained through the high conductivity planes, which are spaced at 1,000 foot intervals, and we can indicate the relatively stable water level in these planes. Also note that there is a distinct water level down here in the SRV, which is lower than the water level in the fracture planes. This is because the wells are much more extensively connected to the SRV than to these discrete planes, so the wells are draining the water from the SRV, and the SRV is then being recharged with water from the fracture planes. This supports a steady, nearly 100% water saturation around the deepest pair of wells. Here we can observe the flow of water entering the SRV and the fracture plane, stage by stage, toe to heel, filling up the fracture system, and then being depleted as the wells transition from injection into production. Observe the highly dynamic and interconnected way in which the two fracture systems interact. The validity of this conceptual model is supported by the findings of Repsol and Sandridge in the Mississippi Lime. In a field experiment with 3 wells in a similar geological setting, deeper wells were used to collect excessive water. Having obtained our calibrated reservoir model, we performed a number of sensitivities and forecasts to explore superior strategies for developing this area. The primary variables we considered were fracture spacing and injection volumes, which usually trade off against one another in unconventional plays, with greater injection volume requiring a wider well spacing, all other things being equal. Here we see the results of several forecast scenarios involving 4 well systems, with 2 wells in the upper Osage and 2 in the lower Osage. We observe very uniform oil production behavior across all cases. These first 6 cases used 1,000 foot spacing between wells in plan view, and these next 3 cases used 700 foot spacing between wells in plan view, with a range of injection volumes. The wells at the widest spacings and the lowest injection volumes performed the best in terms of oil EUR. In fact, since the best case is at the leftmost extreme of the parameter space, this chart suggests that the optimum well spacing is even wider and the optimal injection volume even lower than what is explored here. We begin our investigation with an idealized staggered 4-well system with 2 wells in the upper Osage and 2 in the lower Osage. For all forecasting runs, we take a slice of the model encompassing 2,000 foot of wellbore, which includes 2 fault planes. Observe that the breakdown pressure for each stage is roughly consistent with the exception of stages falling in or near the high conductivity fault planes. These stages have very low peak pressure. Here on the left side, we have the cumulative volumes of water, gas, and oil for one of the upper Osage wells over a 5-year forecast. This well produces some early water, which cleans up. The well effectively becomes a gas well beyond 7 years. The shallowest well, on the right, produces minimal water and becomes a gas well in 1 year. In contrast, here on the left we see the cumulative volumes of water, gas, and oil for one of the deeper wells in the lower Osage. For the first 6 months, the well produces only water and subsequently starts producing oil without much gas. On the right side, we have the performance of the deepest well. For the first 4 months, it produces only water, then produces oil without much gas for about 3 years. However, after 3 years, it continues to produce water, but not much oil beyond this point. Overall, this behavior is due to the fact that the water has slumped down into the deeper wells while the oil has migrated upward through the fault plains. The gas has migrated upward most dramatically, leading the shallowest wells to gas out. Another factor of critical importance is that the segregation of water and oil is ongoing. The water that collects around the deep wells is not merely the injected water, but is in fact continually recharged by the formation water, which flows out of the matrix into the fracture network and then slumps through the fault plains into the deeper wells via buoyant forces. Here are log-log plots for the oil on the left and gas on the right for one of the shallow upper Osage wells. Note the erratic nature of the oil and gas rates when viewed in a log-log plot. The highly interconnected nature of the 4-well system renders attempts at RTA-style curve fitting relatively ineffective. Here, we further see log-log plots of the oil rates for the other shallow well and the 2 deeper wells. Note that the start of the oil production in the lower wells is delayed due to early water production. Again, it is very difficult to identify a meaningful quarter, half slope, or unit slope curve fit due to heavy interference and fluid segregation between wells. Applying a decline curve fit to these wells would not be advisable. Next, we consider the performance of a 3-well system in the Osage, otherwise identical to the previous, except with 2 shallower wells and 1 deeper well. Here we compare the performance of the 3-well system against the 4-well system. On the left, we have the total system cumulative production curves, summing the production of all 4 wells in the 4-well system for water, gas, and oil. The 3 curves on this plot correspond to high, moderate, and low injection volumes. The lowest injection volume yields the best net oil production because there is less water occupying the fracture network. On the right, we have the same plot layout, but for the cumulative production behavior of the 3-well system. Again, we contrast high, moderate, and low injection volumes, but find in this case that oil and gas volumes are not impacted by injection volume. The total water injection in a 3-well scenario is not so excessive as to hamper net pad performance. Next, we will consider a 2-well model with 1 well in the upper and 1 in the lower Osage. For the moderate injected fluid volume design, this plot compares the cumulative production performance of the 2, 3, and 4-well cases. The 2-well system produces more net oil than the 3 or 4-well cases in a 5-year time frame. For this geologic description with these completion practices, minimizing the number of wells may be the most attractive solution. The reservoir is simply too well connected with natural faulting to support high well density. Next, we move on to an analysis of the Meramec. This model is similar to the previously discussed Osage model, except the petrophysical properties are populated from the distribution characteristic of the Meramec. Most importantly, in this Meramec model, there are no discrete fault plains. In this model, we are exploring parts of the stack that are not so thoroughly faulted as our original study area. However, we are still interested in probing the water-oil flow dynamics of this model. An important driver of performance in this kind of unconventional reservoir is the presence of mobile formation water. The stable water cut in unconventional wells is strongly determined by the fraction of mobile water relative to mobile oil. We see in this plot that cases with even slightly different mobile water saturations, for example, 15% mobile water for the red case and 17% mobile water for the blue case, yield dramatically different results in terms of oil EUR over a 5-year time frame. Now we examine the single well behavior of a Meramec proxy system for a 20% mobile water saturation. The higher water injection case placed in the upper part of the formation is contrasted with the lower injection volume case placed deeper in the formation. Note that the higher injection volume case produces more water but also more oil in a 5-year time frame. The choice between the 2 cases is less clear due to acceleration and will depend on economic factors. When placing 4 wells in the Meramec system, again with 2 in the upper zone and 2 in the lower zone, with low, moderate, and high injected water volumes, We observe comparable volumes of oil for all 4 cases in a 5-year time horizon, and a significantly larger volume of flowback water in the higher injection volume cases. This system does not benefit from a high injection volume. Based on the assumption of a low injection volume for all wells, while varying the well count, we find a linearly increasing system-wide oil EUR with each additional well up to 4 wells per section. Adding more wells beyond 4 may be economically justifiable, perhaps up to 6 wells per section. The later drilling of infill wells is a common reality in unconventional reservoirs. Here we examine the impact of producing one well for an interval of time and then commencing stimulation and production of the other 3 wells. Timing of well completion does not strongly impact net system oil and water EUR, but does impact net gas recovery, because more pressure depletion at an earlier point in time means more gas evolution. In conclusion, in some regions of the stack play, Osage series carbonates exhibit signs of high conductivity conduits. Indication of the presence of these flow features includes mud losses while drilling, anomalously low breakdown pressures during fracture injection, geological interpretations indicating faulting, very high water saturation in deeper wells in a given well pad. Where high conductivity conduits are present, development will benefit from lower injection volumes and wider well spacings. In some circumstances, it may be prudent to avoid drilling the deeper wells in a wine rack pattern. Standard conceptual models such as drainage area or stimulated reservoir volume should be regarded with caution, as their application may lead to misleading expectations in regions with heavy faulting. Well performance in the stack play is strongly influenced by the dynamic behavior of water in the fracture network. Thank you for your attention. If you're interested in finding out more about the services we offer, please contact us at solutions@nitecllc.com or visit our website at www.nitecllc.com.